We're going to look here at the second case of solutions for homogeneous second-order linear differential equations. This is when we have repeated or coincident roots as the solution to our auxiliary equation. Now, there's a rule we have to remember and recall in order to be able to look at these solutions and work them through. And that rule is that if y equals ae to the mx is a solution, so is y equals ax e to the mx. So if we have y equals ae to the mx as a solution, we know then that a times a m squared e to the mx plus b times a m e to the mx plus c a e to the mx equals 0 is a solution to our second order differential linear equation. Taking out e to the mx and the a as a factor as well, we know we've got am squared plus bm plus c times a e to the mx equals 0, as we had previously. So for that to be the case, we know that a m squared plus b m plus c equals 0. So we know that works. Now we're going to consider the case where it's repeated or coincident roots. What that means is that in a quadratic formula, b squared minus 4ac equals 0. Now if that's the case, this reduces to m equals negative b over 2a. Now I can rearrange this to make that 2am plus b equals 0. Now this here is a condition that will come into play in a minute, but we have to know that this comes into play if we've got coincident roots in the solution y equals ae to the mx. Now what we've said is if this is a solution, so is y equals ax e to the mx. Well, let's have a look at that. So we know y equals ax e to the mx. dy by dx is equal to a m x e to the mx plus a e to the mx. This is just using the chain rule because we've got two functions dependent upon x multiplied together. Factorise it, what I'll end up getting is mx plus 1 a e to the mx. Take the second derivative, so d2y by dx squared. What I'll end up getting is mx plus 1 times ma e to the mx, then plus the second part of my derivative, which is derivative of the bracket here, m, times a e to the mx. So there's me got my derivatives there. What I can then do is plug it all together into a second order differential equation. If I were to do that and play the parts about, take common factors of a, b and c as my coefficients, what I'd end up getting is I'd get a times a x m squared e to the mx it's going to then be plus a m e to the mx, then plus another a m e to the mx, I've then got plus my b times the first derivative, so that's going to be plus my b times the mx plus 1 a e to the mx, then plus my c times the original equation, plus c times a x e to the mx, and I know that then equals 0. Now that's a lot to take in there, but if I were to simplify the parts down, I can multiply this bracket and this bracket out by the a and the b, and then gather everything that's got an ax e to the mx together and an a e to the mx together. What I'll end up getting is I'll get ax e to the mx, close bracket, times am squared plus bm plus c, then plus a e to the mx times 2am plus b and I know that that equals 0. So what we now know is that I've got this as my overall solution. Now, we know that these e to the mx parts cannot be 0. They can't. So what we need to do is set a m squared plus bm plus c equal to 0. We know that here from the auxiliary equation. So that part there is equal to 0. However, we've got a e to the mx times 2am plus b. Now, the condition we're looking at is assuming we've got repeated or coincident roots. So that means that from this part here, the 2am plus b equals 0, we know that this little bit here is also equal to 0. So what that means is I can now take the fact that both of these are solutions. So I know that y equals ax e to the mx is also a solution to my equation. So what that means is I've got two solutions, so ax e to the mx and an ae to the mx. So in order to satisfy this, I'll give them both an arbitrary constant that's different from the other. So I know my solution is going to be y equals ae to the mx plus bx e to the mx. Now another way to look at this is to think that we want two different parts of a solution to this, and if I don't separate them like this and make this one a distinct bx times e to the mx, what I'm going to get is a times e to m1x plus b times e to m2x. And if I combine that, I'm only going to get one part of a solution, but I'm going to get the two coefficients a plus b clubbed together. So it's not going to have two terms in it like I need for my final solution for this type of equation. Now, as we previously covered, the steps to solving it, they're actually the same. Yeah, they're relatively similar to what we had before. The only difference is this part of the solution here. So what I'm going to do is I want to show you a particular solution for an equation that involves this type of condition. So let's imagine I want to find the particular solution to 4 times d2y by dx squared, take away 4 dy by dx plus y equals 0, and the conditions that I'm going to give you are these ones here. Now again, they'll come into play once we're finding the particular solution, i.e. the coefficients a and b. So what we have to do is start off the same way we did before. Get our auxiliary equation. Now again, look at the coefficients of each part here. Now if I do that, I'll get 4m squared minus 4m plus 1 equals 0. What I can then do is factorise this, and what I'll end up getting is that 2m minus 1 squared equals 0. So what I'll end up getting is that m equals a half. So I'll only get one solution where m equals a half, and that then means that I've only got one root to my equation, so I have to take into account the fact that I'm going to have y equals a e to the mx plus bx e to the mx. This question might be phrased slightly differently. It might have a first part that says prove it's got coincident roots, and if that's the case, focus on the discriminant of this, because you know the condition is b squared minus 4ac equals 0. If it does that, do that first part, and then it'll tend to go in to find the general solution, hence find the particular solution. In this case, we're going to just jump straight to finding the particular solution, and again, because we've got two coefficients here, we need these two conditions. Substitute the m equals a half here, because first we need the general solution, and we get y equals a e to the half x plus bx e to the half x. So what I'm now going to do is use my initial conditions in order to solve these. So x is 0 and y is 3, so let's start with that. If I substitute x is 0 and y is 3 into here, this term here with the b will disappear because it's bx, so that is b times 0, which will go. This is then ae to the half x, so it's going to be ae to the 0, so that's just going to give me a, and I know y is 3, so I know y is equal to 3. So that's if I take the x is equal to 0, y is equal to 3 condition. What I'm then going to do is take the second condition, is x equals 0, and dy by dx equals 1. So first thing I have to do is calculate the derivative of this here. So from that, I know that dy by dx is equal to half a e to the half x plus b e to the half x plus a half b x e to the half x. What I'm going to do now is substitute in the conditions. X equals 0, dy by dx equals 1. So x is 0, dy by dx equals 1. And what that means is I'm then going to get 1 equals, well, if x is 0, that goes. So I'll get a half a, then plus b, and this whole term here just disappears. Now, at this stage, I know that a is equal to 3, so I can just substitute it into here. So I can just simply say that b is equal to 1, take away a half a, so it's equal to 1 minus 3 times a half, so take away 3 over 2, which is just negative a half. So that's my initial condition used to solve and get me my coefficient b. What I can then say is fine, therefore y equals a e to the half x, so 3 e to the half x, plus bx equal to the half x, so it's then minus a half x e to the half x. So I've got my particular solution for those sets of conditions that I was given for that equation. And again, a key thing we have to remember that I've got to take into account is to get the right powers and the right coefficients associated with each other, as well as the coefficient x. So my a was 3, that has to go with just the e to the half x. My b, which was negative a half, has to go with the x e to the half x. You can't mix those two up. We have to make sure we get them right, as we explained in the previous examples when we had our first case of two real distinct roots.